Welcome to chromatography. In this video, we'll look at the principles and the theory of chromatography, and the principles behind thin layer chromatography and high performance liquid chromatography, also known as high pressure liquid chromatography. In class, what we'll do is we'll look at the qualitative and quantitative analysis using these types of chromatographic techniques. So imagine you've got a ship. So let's draw a little bit of a ship here, and it's in some water. So we're just going to get the blue and draw some water here. So you've got a ship and it's in a bunch of water. And the good thing about the ship is that it's got a sail, which means that what can happen is that if there's a wind blowing the ship to the right, it means the ship is going to be able to move to the right, which is really cool when this happens on water. But let's say we have a situation where I get rid of the water and the ship instead is going to be on a bunch of bitumen road. So we have a bitumen road right here and it's on the road. This time I get a fan, or I get some wind, or I get some wind and I blow the ship across the road. It's not going to move at all. So this is a bit unfortunate, but we can take away some principles from this, which is what? The ship has a bunch of properties, and it's got an amount of friction between the road and, well, the surface of the ship. So in this situation, when I've got the hull of the ship here, there's a lot of friction between the road and the ship, which stops it from moving very far. But when I have a situation where I get the ship and I put it on, let's say, some water. So let's say we go ahead and get some water here. In this situation, there is a lot less friction between the boat and the water, which means there's a lot less friction between the two of them here, which means what? Which means that when the wind blows, the ship can move across in a particular direction without being stuck to the road. Alright, let's say I've got a race here, and we call this the Great and Amazing Race. And in this great race, what we have is we have a massive draft coming from the side. Okay, so we first of all have a massive draft, so we can say that this is the wind. And then we can also say that we've got a couple of different vehicles that are starting in this race. We have our ship here, we have our car, and we have our bicycle. Okay. When I start this race and the wind blows all of these forward, what happens? Well, I know with the ship has a high amount of friction between the road and the hull. So when the wind pushes the ship's not going to move very far at all. So the ship's going to move maybe up to here and then it's going to stop. Well, it's going to move very, very, very slowly because of the friction between the wooden hull of the ship and the tar road that we are racing on. With the car is very heavy, so it's also got a lot more it's got like a reasonable amount of friction between the car and the road, but it's not as much friction as the boat has with the road. So the car, if it were to race, it would go, a fair amount, maybe up to about here. Whereas the bicycle has the least amount of friction between its wheels and the road. So when the wind starts blowing the bicycle forward, since it has the least amount of friction, it means that it will go perhaps the most far out of all the different vehicles. What is the principle to take away from this? The principle is to take away from this is that each of these vehicles have a different amount of friction with the particular road that they're racing on. So because of this, when we start them here and we push all of them along, what happens is that these vehicles separate. They separate. Why? They separate because of their different affinity to the road. So some vehicles have a higher affinity with the road, such as the boat. It has a higher friction with the road. Affinity, remember, just means like attraction to. Alright, so think of it as the friction. So the boat has a higher affinity with the road, so a higher amount of friction, so therefore it doesn't move as far. But the bicycle has the least amount of friction with the road, so it moves the furthest out of all of them. So as a result, we get the boat separating from the car, separating from the bicycle. Alright, let's see what happens if we change the situation to a slightly different situation. Over here, we replace the road with the ocean. This time, let's think about it. And I know that you're going to have to stretch your imagination a little bit, but just bear with me for the sake of the principle. We've got a ship here, and the ship has low affinity, so low friction, to the water. So that means that when the wind blows here, the ship can go really far because it floats on the water and keeps going. With the car, when you put it in the water, it doesn't move very far at all. And the bicycle might have a little bit more luck. Maybe it'll go over here. But we can see here, what we see here is that when we change the surface of the race or surface of what these things are on, right? We change, these different chemicals have a different affinity or a different amount of friction or attraction to the water. The ship here can glide over the water. The ship here can glide over the water, but when it was placed on the road, it could not move very far at all. Whereas the bicycle could move really far on the road, but in the water, it's not going to move very far. The car could move a moderate distance on the road, but when it's on the water, it can't move very far at all. So we see that when we change the surface, basically, we see that these different chemicals have a different affinity to different surfaces. Alright, so we need to apply some terminology and understand what's happening with this example. So in our example, we had something like a road, we had some vehicles, and then we had something that pushed the vehicles, so I'll call this the wind. Alright, and we know that because different vehicles had a different amount of friction with the road, they separated. Well, in chromatography, this is obviously analogous to what we look at in chromatography. In chromatography, we have things called the components. So I'm just going to change the color here actually let's change it to this. We have something called the components. So the components are the individual things or individual chemicals that we want to separate. So components are the chemicals in the substance which we want to separate. Okay, so we might start off our investigation with a jar of unknown liquid. So this is a jar of unknown liquid. And we might ask ourselves, well, I want to know how many different chemicals are there in these liquids. Or I might ask myself, what chemicals are in these liquids? Or in this liquid, what chemical is in this liquid? Okay. And then if I did that, what the individual chemicals that were in the liquid would be called the components. The components would be the individual chemicals that make up this unknown liquid. So in our example, our components are vehicles. We have got 3 chemicals here. We've got the boat, the bicycle, and we've got the car. Now, the boat, bicycle, and car, they travel across this stationary chemical, which we see as the road. Okay, so the road is the thing that these things travel across, and these vehicles themselves have different amounts of friction with the road. In chromatography, the road is known as the stationary phase. Phase. Okay, and the stationary phase is simply defined as the chemical that does not move. So the chemical that does not move in chromatography, that is the stationary phase. There's also another phase, which is this wind here, which is pushing the chemicals along the stationary phase. We can see that the wind is moving. So the wind is going to be known as the mobile phase. And the mobile phase is simply going to be the chemical that moves. Okay, so we have 3 things that we need to look at so far. 1, which is the components, the individual chemicals that we want to separate from our mixture. 2, the stationary phase, which is a chemical in the chromatography setup that does not move. And 3, the mobile phase, which is a chemical in the chromatography setup which does move. Okay, so the principle behind chromatography is this, and this is a very important point. A very, very, very important point, and the point that they will ask you. The question will be this: why do components separate? In chromatography, okay, that's the question that's the big $1 million question. Why do components separate in chromatography? And the reason is this, okay, the reason that you want to write on the paper is because the components separate because different components have a different relative affinity to the mobile and the stationary phases. That's the reason. The components separate because different components have a different relative affinity to the mobile phase and the stationary phase. So to translate that into our racing example, different components, so different vehicles here, or different chemicals, if we look at the example, if we look at it in reality, they have a different relative affinity to the mobile and stationary phase. Basically, that means that each different chemical has a different attraction to the road and the wind. Okay, so we're saying here that the different vehicles here, like the boat has a strong attraction to the road. It's got high friction and will not move very far. And then the car here and the bicycle have a lower affinity to the road. In other words, they have a lower affinity to the stationary phase. So there's not as much friction between the road and the components, or the road and the car and the bicycle. So therefore, they move a lot faster. So we see that the affinity of the, let's say, bicycle relative to the affinity of the boat is different. So therefore, they separate when they do that, right? And also, we also realize that different vehicles will have a different affinity to the wind. So for example, one chemical might be more attracted to the wind, so the wind pushes it better. So for example, you think if a boat had a bigger sail, it would capture more wind and therefore be pushed further along. So we see that based on the vehicles or the chemicals' affinity to the mobile phase, which is the wind, and the stationary phase, which is the road, based on the differences between these attractions and friction, as an explaining word, then because of this, they will separate. Let's look at two principles to chromatography success. The first one is that like dissolves like. This means like is attracted to like. So what is a like substance? What this means is that if I have a polar solvent, right, it will be able to dissolve a polar solute. So something polar will dissolve another polar thing. And likewise, a non-polar thing will dissolve a non-polar thing. So like is attracted to like. This also means that a polar substance is attracted to another polar substance. And a non-polar substance is attracted to a non-polar substance. What's the application of this? If I have my road here as my stationary phase, so SP for stationary phase, and remember that's my road, and let's say this is a polar substance. I'm going to draw a P here to represent polar. If my component is a car, let's say my car here is a component, and this is also a polar component. What this means is that since I know the stationary phase is polar, they will tell you this, or we'll talk about how to work out this, whether it's what the polarity of the stationary phase is later. But let's just say that the stationary phase is polar and the car or the component is also polar. This means that since both of them are polar, our rule is like attracts like, or like dissolves like, which means that the polar component will be very attracted to the polar stationary phase. So therefore, it's going to be stuck and have a lot of friction with the stationary phase, and it's not going to move very far. However, if I have another car, and this other car is non-polar, okay? This means that since it's non-polar, it will not have a lot of attraction to the polar stationary phase, and it will have less friction than the polar car. So therefore, it will move a lot further. That's the principle between like dissolves like. The second rule that we need to know for chromatography success is the principle of adsorption and absorption. So sometimes these are stylized or spoken as adsorption and absorption. What's the difference? Adsorption, adsorption, refers to when a substance expresses its attraction to another substance by forming surface-to-surface bonds. What does this mean? Let's say I have a chemical here, and the chemical is a brick. Okay, the chemical just is a chemical that shaped and looks like a brick. So it's a solid chemical. Okay, and let's say I have another chemical here, which is some, I don't know, they're these little particles. Okay, so these particles here, if they are attracted, let's say these are polar particles over here, so P for polar, and the solid brick is also a polar chemical. When these two polar things are attracted to one another, this little particle here cannot be immersed or dissolve into the solid. It just can't. So what happens is that this little particle, when it comes and gets attracted to the solid, it will stick to the surface of the solid like this. Okay, so when we have something sticking onto the surface of a solid, well, yeah, most likely a solid or a very, very thick liquid, we call this adsorption. So adsorption is when there's the formation of temporary surface to surface bonds between chemicals. Okay, so that's adsorption, when we form surface-to-surface bonds temporarily. Because a moment later, what happens is that these bonds break and the particles come off. And when the particles come off, this is going to be known as, cleverly, desorption. Okay, so adsorption, when something adsorbs onto the surface of something else, it sticks to the surface by forming temporary surface-to-surface bonds. And when something comes off a surface, basically these surface-to-surface bonds break, and we get a situation known as desorption. Now the next idea is what is absorption. So absorption is a situation where we have most of the time a liquid. Okay, so if I have a liquid here, let's say this is a jar of liquid, and I get some Milo powder, right? And I put the Milo in, assuming that the Milo dissolves, because sometimes it doesn't, it just clumps up. But let's just say the Milo dissolves. So the Milo dissolves and is taken into the substance of into the substance of the water. So when we get a situation of absorption, what we see is that one chemical, right, is taken wholly into the substance of another chemical, and that is absorption. So absorption is when a chemical is taken into the substance of another chemical. Okay, and this is analogous to dissolving. Okay, so when something dissolves into something, it is absorbed. But when something sticks to the surface of something else, it is adsorbed. Now, what is the application to our chromatography? The application is this. We have a stationary phase, right? So remember, the rhode is the stationary phase, the chemical that does not move. And we have a bunch of substances that are traveling along the stationary phase. And remember that based on the amount of friction that these substances have with the stationary phase, so in other words, the amount of affinity, okay, affinity is the correct word to use, the affinity that these have with the stationary phase, that will determine how far these things move. So, how does this affinity manifest itself? The answer is this. If the stationary phase is a solid, the components will adsorb onto the surface of the solid and get stuck there. If the stationary phase is a liquid, the particles will dissolve into the liquid and stay there. So whether or not a particle or component adsorbs or absorbs, so that is adsorbs or absorbs, depends on whether or not the stationary phase is a solid or a liquid. So adsorption occurs when the stationary phase is a solid, And AB sorption occurs when the stationary phase is a liquid. Alright, let's look at planar chromatography principles. Planar chromatography just means that the chromatography occurs on a plane, so like a flat plate. And this is the type of chromatography that we use in TLC. In planar chromatography, what we have is we have a plate as a stationary phase. So most of the time, what we will have is we'll have a glass plate that's covered in powdered alumina, Al2O3, or silica. And the thing to remember is that these are very polar. Okay, so this is our stationary phase. Our stationary phase is a glass plate of alumina or silica, coated with alumina or silica. The mobile phase is this here. We can call this the solvent. Right, so this is known as the mobile phase, also known in this context as the solvent. And this is usually a non-polar solvent. Something like a ketone, or sometimes an ester, or something like that, or like a thick, big, heavy hydrocarbon or ester. So non-polar solvent and a polar plate. What we do is we get the mixture that we're trying to analyze, and we put a bunch of it over here in a big dot. Okay, remember, chromatography is a separation technique. So we have a substance with a bunch of chemicals inside the substance, and we try to separate those chemicals from the substance. So the dot where we place the substance that we're analyzing is going to be known, or the sample is going to be known as the origin. Okay, so the origin is going to be where we place the sample of chemical. So this is where the sample that contains all the components are. So what happens? What happens over time is that there is a process whereby I've actually drawn this incorrectly. What we should always remember is that the origin should be placed above the level of the solvent. So the origin should come and go up there. The reason being is if I put the origin below the level of the solvent will dissolve the entire origin. So that was a mistake on my part. It should be right here. Cool. So what happens is this. Over time, we get the solvent creeping up the glass plate. And this is done via a process known as capillary action. You don't need to know it, but we can discuss this in class if you want to. So this is known as capillary action. So capillary action is the same mechanism by which if I were to get a bunch of paper towel and put one corner of the paper towel on a bit of water, the water would kind of quickly soak up and creep up the paper towel. So the same kind of thing is happening here. As the mobile phase goes up, what happens is that the mobile phase will come into contact with the origin, and in doing so come into contact with all of the components inside the origin. What will happen is this. The components will play a game. The component, right, let's say we have let's say one of the components here is a non-polar component. What happens is that as the solvent creeps up, the non-polar component will spend some time dissolved into the solvent. So the non-polar component will dissolve into the solvent. When it's dissolved into the solvent, it will creep up a little bit because the solvent is moving up. A split second later, the non-polar component will have some little attraction to the stationary phase. Remember, even though this is non-polar and the stationary phase is polar, there's still a little bit of friction between the non-polar component and the polar stationary phase. So this little thing will have a little bit of friction with the stationary phase and adsorb onto the surface of the stationary phase. So the non-polar component plays a game where it spends most of its time, so 80% of its time is going to be dissolved in the solvent or the mobile phase. So 80% of the time it's dissolved in the mobile phase, and because the mobile phase is moving, the component will be moving up. But then maybe let's say 20% of the time it will be adsorbed. We say adsorbed because the stationary phase is a solid, so 20% of the time it will be adsorbed onto the surface of the stationary phase and not moving. Let's compare that to another example. So let's say instead what we have is we've got a polar component. So over here, let's say we have a polar component. If there's a polar component also in here, what's going to happen? Well, the polar component is going to be very attracted to the polar stationary phase. So because of this, the polar component is going to spend maybe 80% of its time adsorbed onto the stationary phase, and as a result, not moving, because it's got a lot of friction with the stationary phase. It's got a high affinity. However, 20% of the time, it will be dissolved in the mobile phase, okay, because it still has some attraction to the mobile phase. So 20%, it will be in the mobile phase and moving. So if you have a look at this, the polar component is going to spend most of its time not moving and attached to the stationary phase, whereas the non-polar component is going to spend most of its time dissolved in the non-polar solvent. So at the end of the day, what we get is we get a situation where the origin was originally here, and you would get ideally 2 dots at the end of the situation, at the end of the chromatography session. This dot here would be this one would be the less polar substance, and this one over here would be the more polar substance. Because the more polar the substance, the more attraction it has to the stationary phase, and therefore the more time it spends stuck onto the stationary phase and not moving, so it doesn't move as far. So this is like the boat in our race example. Whereas the less polar one will spend less time stuck onto the stationary phase. Remember, the stationary phase is polar, and more times dissolved in the mobile phase. Remember, the mobile phase is non-polar, so therefore it's going to move a lot further. It's going to have less friction. It's going to have a better sail, so the wind will blow it further, and it's going to have less friction with the quote-unquote road here of the stationary phase. So it moves further than the more polar one. So you can see polar has moved this far, and the less polar one has moved this far. The last point to mention is that the solvent also travels up over time. So the furthest point that the solvent reached, remember, as this reaction is going, the solvent is just creeping up like this, right? So when the reaction finishes, the furthest point that the solvent goes is known as the solvent front. Solvent front. Okay, cool. And that's our introduction to how we use planar chromatography for separation. Alright, how does column chromatography work? The way column chromatography works is that instead of having a plate as your stationary phase, what you have is you have little balls of solid alumina or silica that could be coated in a thick viscous liquid. Right, sometimes it's coated in a thick viscous liquid, sometimes it's not, but the idea is the same. It is solid alumina or silica. Okay, and this is packed into a column, as we can see here. And what happens is this. What happens is that the stationary phase is our alumina and silica, and the mobile phase is actually introduced into the solution and constantly pumped into the solution and pumped out of the solution, like this. So the mobile phase is the same. It's a non-polar liquid. So mobile phase equals a non-polar liquid. And that is pumped into the column and pumped out of the column at the same rate. Now, the mobile phase in this situation has a number of different names. We can call it the mobile phase. We can also call it the solvent. And we can also call it this new word eluent. Okay, the eluent, to elute something, means to pass a liquid through a tube. So an eluent is the liquid that we add into the tube so that it may be passed through the tube. So you'll hear the mobile phase being called mobile phase, the solvent, and the eluent in column chromatography. So what happens is this: the mobile phase is pumped in and pumped out at the same rate, and then at a particular point I have a bit of a sample, and I put the sample in here. Okay, let's say my sample contains two chemicals, okay, A and B. So the sample contains chemical A and contains chemical B. Let's say A is polar and B is non-polar. What happens? I remember that solid alumina and silica is the stationary phase, and that these are polar. So therefore, let's say this is alumina and alumina inside the tube. When I get my when I get this sample and I stick it in, what's going to happen is that most of the polar A is going to be stuck and spend the majority of its time stuck onto the surface of the polar alumina, because remember, like dissolves like. However, when I get my non-polar B, the non-polar B is going to go right past. So let's have a molecule of non-polar B here. It's not really going to be attracted to the alumina. So when it encounters the alumina throughout the journey, most of the time it will spend dissolved in the non-polar mobile phase and just consistently flow down. So what we get over time is we get a situation where we start off with A and B being at pretty much the same place. So A is over here and we get B over here at the very start. But over time, what happens is that the B will remain stuck. So let's say they move down a little bit more. The B is now going to be over here. But the chemical B moves a lot slower than chemical A. Chemical A, my bad. This one's chemical A here. Chemical A is stuck onto the solid stationary phase, so it moves a lot slower than chemical B, which can just move straight past. Sorry, my mistake. So chemical B over here, by the time chemical A has reached here, right, chemical B has reached all the way down here. So we can see that as a result of this setup, we get separation. And that's the introduction to column chromatography.